All right. Okay. I hope you can see the first page now.
Yeah.
All right.
Okay. 1 second. So the live stream is online. Let's also record. Yeah, we can. So, all right. Welcome, everyone. It's my great pleasure to welcome all of you to today's InfoSec research seminar. Our speaker today is Aydin Abadi, who is a research fellow at UCL, and he joined us recently. So welcome at this point. And prior to his position at UCL, Aydin had a lectureship and research associate position at the University of Gloucestershire and Edinburgh. And while he was at Edinburgh, he was working with a blockchain technology lab, where he did research on blockchain technologies and cryptography, and also developed the corresponding decentralized applications to it. And his PhD he received from the University of Strathclyde in Glasgow, and he worked on secure multi-party computation. And today, Aydin will present to us one of his latest work on multi-instance publicly verifiable Timelock puzzles and their applications. Aydin, the floor is yours.
Thank you. Hi, everyone. As is mentioned, I'm going to briefly talk about one of our recent work titled Multi-Instance Publicly Verifiable Timelock Puzzle and its Application. So the focus is on Timelock Puzzle. It's a joint work with Agilosquares. I did this work when I was at Edinburgh. And the paper with the same title appeared in Financial Crypto this year. So Timelock puzzles are interesting cryptographic primitives that allow sending information to the future. They enable a party to lock a message such that no one else can unlock it until a certain time passes. In general, Timelock puzzles can be categorized in two classes. Class 1, those that use a trusted third party for time release of a secret key. And this class is not the focus of our work. And class 2, those schemes that do not involve a trusted third party, which is the focus of our work. In regular encryption scheme, like RSA, LGAML, and so on, a ciphertext cannot be decrypted without knowing the secret key. Given the ciphertext, even a polynomial time adversary cannot decrypt the ciphertext. However, in Timelock puzzle protocols, the recipient of the ciphertext, or the solver, can eventually decrypt a puzzle, given only this, the puzzle or the ciphertext and some public information. So once the solver receives the locked message, it continuously works on it until it finds the secret key and then unlocks the message. The amount of time needed to unlock a message is fixed and known ahead of time. So in general, there are two parties involved in a Timelock puzzle protocol, a client and a server or solver. First, in the protocol, the client generates a public set of public parameters and set of private parameters. Then it encodes the message into a puzzle such that it should be revealed after a certain time. So here the puzzle is O, double.O, and I'll call it O, and message which is encoded in the puzzle is M. Next, it sends the puzzle to the solver. Upon receiving the puzzle, the solver, as I mentioned, continuously works on the puzzle to find a secret key. Given the secret key, it extracts the encoded message. The Timelock puzzles that do not involve a trusted third party are often based on sequential squaring. Sequential squaring is believed to be secure against a solver who may have access to many computational resources that are run in parallel. That means if a solver possesses many processors, it cannot reduce the time required to solve a puzzle. Of course, it can reduce to some extent, but cannot significantly reduce. The overall idea is that a solver is given a public base. Here is R, time parameter T, and public modulus N. It needs to find R to the power of 2 to the power of T. This is its goal. So in this scheme, in general, the solver raises R to the power of 2 mod N. Then it needs to repeat this process. So given the solution, it raises the solution to the power of 2 to the power mod N. And it repeats this process over and over for T time. So this number of squaring is T times. In general, it is believed that there is no shortcuts to find the final result without doing all the steps sequentially. Otherwise, the puzzles could be solved much faster. Let's have a look at one of the well-known RSA-based Timelock puzzle proposed by Rivers and Shamir. In step A, a public modulus is generated. It's a RSA public modulus. And in step B, the public value T is generated with a product of two values, and delta, which is a time period within which the message should remain hidden, and S is a maximum number of squaring per second that can be performed by a solver. So it's assumed that we know this value. And in step E, value A, which is the result of 2 to the power of T mod phi of N is calculated. Calculating value A is kind of fast if someone knows phi of N. So let's move on to the next phase, which is generating a puzzle. So I'm just highlighting the important parts of this algorithm. In step A, the message M is encrypted using a symmetric encryption. In step B, the secret key for the symmetric encryption is masked. It is encrypted again, using value R to the power of A. Recall that A was generated in the setup phase. And in step C, the puzzle is set. So the puzzle contains the masked key and the ciphertext, the message which is encrypted. And in the next phase, which is the solving puzzle, so the solving puzzle is performed by a solver, obviously. The solver continuously raises R to the power of 2 mod N for T times, as I explained earlier. Once it finishes the squaring, completes all the T squaring, it can unmask the key, the secret key. Given the secret key, can decrypt the ciphertext and extract the message M. So in general, Timelock puzzle have many applications, such as e-voting, fair contract signing, release of confidential document or file over time, or sealed bid auctions, to name a few. Over the last 2 decades, various Timelock puzzles have been proposed. However, the existing schemes are not suitable for the case where a solver is given multiple instances of a puzzle. Is given many puzzles at once and must unlock them over time, at different point in time. If the existing schemes are naively used in the multi-puzzle setting, as I explained before, then the solver has to start solving all puzzles right after it receives the puzzles in order to solve them on time. This ultimately imposes significant computation costs and demands a high level of parallelization. Let's have a closer look at this problem. Consider the case where the client wants a solver to learn a vector of messages, M1 to MZ, at time F1 to FZ. So what I mean here is that M1 needs to be discovered at time F1, and the last message, MZ, needs to be discovered at time FZ, right? And Fi or Fj is bigger than Fj minus 1. Okay. The client is available and online only at time F0, which is smaller than F1. Okay. So I'm going to explain the naive approach. So in the multi-puzzle setting, where we want to use existing schemes. So here, the client needs to generate multiple puzzles for each message. And then, yeah, it's got a set of puzzles from O1 to OZ. The client sends all puzzles to the solver. For the solver to decrypt the messages on time, it needs to start decrypting all of them as soon as the puzzles and the public parameters are given to it. If it works on all of them without any break, then it can find the related message on time. This naive approach results in 2 serious issues. Demands a high level of parallelization because each puzzle has to be dealt with separately in parallel to the rest. And a high computation cost, as the solver has to perform high number of squaring to decrypt all messages on time. So this is the total number of squaring or exponentiation required to decrypt all messages, which is high. To address the issue, we proposed and formally defined a primitive called multi-instance Timelock puzzle, which allows composing a puzzle's instances. In this scheme, given the composition, a solver can deal with each instance sequentially. So they don't need to be dealt with simultaneously. Also, we presented an instantiation of this primitive. So a multi-instance Timelock puzzle is secure if it satisfies 2 properties: solution privacy and solution validity. I will briefly explain each property. Solution privacy means that ith solution should not be found earlier than the time initially allocated for that message or for that puzzle. So putting it in a more formal way, we define a game in which an adversary is given public parameters. Then the adversary picks a vector of pairs where each pair contains two messages. Then the environment randomly in this vector for each pair picks one of these messages and encode it into a puzzle. It does it for each individual pair. So the privacy requirement is that for each pair of message, the adversary should not be able to find learn which message was encoded into the puzzle, given all the messages in plain text and the puzzle itself. So the probability should not be significantly greater than 1/2. On the other hand, the solution validity means that it must be infeasible for a PPT adversary to provide an invalid solution and convince the verifier. More formally, again, to define this property, we need to define an experiment or game. In this experiment, the adversary is given all these public parameters and it can pick its own message. The difference here is that the adversary is also given the solution, the puzzle itself and the solution. Then it shouldn't be able to convince the verifier who hasn't seen the solution yet with a probability significantly greater than, with a negligible probability. Right, so as I mentioned, also we provided an instantiation of this primitive. So the instantiation is called chained Timelock puzzle, or C-TLP. So some features of these primitive include that these primitive can make black box call to a standard Timelock puzzle, like RSA Timelock puzzle. So the core of this traditional Timelock puzzle remains unchanged, which is good. We don't need to worry about the security of this chained Timelock puzzle too much, because we are using a standard Timelock puzzle. It has been around for decades. Also, the chain Timelock puzzle has a lightweight verification cost. Especially its cost of the verification is very low for verifier, both in computation and in communication cost. Also, the verification allows anyone to check the correctness of the solution. So it supports public verifiability. So our key observation is that in the naive approach, the process of decrypting messages has many overlaps, leading to a high computation cost. I'll show you shortly. By eliminating these overlaps, we can considerably lower the overall cost, both in puzzles solving the puzzle and creating puzzle phases. So if we get back to our previous example where we had Z messages and they had to be dealt with in parallel, then as you can see, for instance, in the first period from F0 to F1, where F0 is a time where all the puzzles are given to the server, then the server starts solving all of them here. As you can see here, all of the puzzles are being computed at the same time. So there are many overlaps in computing this exponentiation, performing squaring. So the question is, we asked was, can we eliminate these overlaps? At the same time, get the same feature, which is solving the puzzle on time, each puzzle on time. So the answer was yes, and the technique to overcome this problem was to chain puzzles. Chaining puzzles seem to be a relatively obvious approach to tackle the issue. However, designing a secure protocol that also makes black box call to a standard Timelock puzzle, supports public verifiability, and has low cost, it wasn't very trivial. So at a high level in our solution, the client first encrypts the message that is supposed to be decrypted after the rest. Then the client embeds the information needed for decrypting that message into the puzzle of the message that needs to be decrypted before that message. In other words, the client generates the information needed for to decrypt message MZ into the puzzle for the message MZ-1. In this way, the puzzles are kind of linked or chained with each other.
So just one quick clarification. Basically, you start at the very end with your chain, and then you compute until you're reaching the head of the okay. Yes,
exactly. So I'll show briefly in this slide. Hopefully, it clarifies things. Mm-hmm. So please recall that we have got from M1 to MZ messages, and we want each M to be decrypted at a certain time. For instance, M1 at F1 and MZ, the last message, at time FZ. To generate a chain puzzle, the client starts from the last message, MZ. Okay. It processes MZ to generate related puzzle. During this process, it also computes a public key for PKZ for that puzzle, for OZ. Then the client moves to the message before that, MZ-1, that is supposed to be decrypted before MZ. It processes MZ-1 to generate a puzzle OZ-1. So as you can see here, the public key for this puzzle has been embedded into this puzzle. Okay. It repeats this process, as you mentioned, until it reaches to the first message, M1, and generates a puzzle for it. During this process, it also computes a public key, PK1, for the first message, or first puzzle, O1. When everything is done, it publishes all the puzzles from O1 to OZ, and also the public key for first puzzle, PK1. So by the end of this process, the client has created a set of puzzles that are somehow chained with each other. In order for a solver to solve the puzzle, it has to start from the first puzzle, puzzle O1, which is the opposite direction of the process in which the puzzle were created. Given PK1, which is a public, and O1, which is the first puzzle, also is a public, and the solver performs squaring, modular squaring, until it discovers the first message and PK2. Where PK2 is a public key for the next message, M2. After that, the solver moves to the next puzzle, O2. It also performs a squaring until it solves the puzzle. Again, the solver repeats the process until it reaches to the end, the last puzzle, which is OZ, and solves that puzzle as well. So by the end of this process, the solver has managed to find all puzzles solution. Right. So you may ask, so what's the difference between this approach and the naive approach in terms of this overlap and computation? So as you can see now, unlike the previous approach, here, once one puzzle has been solved, the solver starts solving another one. So there's no overlap. We don't see any overlap anymore. So the computation cost can be lower than previous scheme, and also the solver doesn't need to have many processors to deal with all of the puzzles. So as I mentioned, this Timelock puzzle, this chained Timelock puzzle, supports public verifiability. So to let the scheme support efficient public verifiability, we use this technique. When the client generates a puzzle for a message, it also commits to that message and put the commitment inside the puzzle, and then creates a puzzle for it. Then client publishes all the commitments so the public can access it. Also, the client sends the puzzle to the solver. Because the puzzle is secure and the commitment is hidden, then given these two sets of information, neither a solver nor the public can learn about the encoded message yet. Usually in commitment scheme, the client who initially commits to the value later on opens the commitment. But in our scheme, the client doesn't open the commitment. Instead, the solver or solvers does it. So the solver finds the solution, extract the opening, and then prove it to the public. So given the opening and commitment, then everyone can check whether a puzzle has been solved correctly or not. So in our scheme, any kind of commitment scheme can be used, such as hash-based commitment scheme, which is very efficient, but in random oracle model, or standard commitment scheme, like Pearson commitment, which requires a couple of exponentiation for each verification. It's less efficient than hash-based commitment, but is in standard mode. Right. So now let's have a look at the chain Timelock puzzle protocol. So again, I'm going to just highlight a few important, a few points that I think is important. First, in the setup phase, as you can see, the protocol makes a black box call to the original to RSA-based Timelock puzzle scheme to generate sort of public and secret parameters. Also, in addition to that, it needs to generate sort of 3 or 4 vectors of secret parameters, which are not needed in the original RSA-based Timelock puzzle. In the next phase, which is generating puzzles, there are 2 points that I want to highlight. One is, again, it makes subroutine black box call to RSA, the well-known RSA Timelock puzzle. And the other one is here, as you can see, each public parameter for the next message, next puzzle, is embedded, is concatenated with a puzzle solution for the current message. And we just concatenate the public key with the message. Also, here we have got D, which is also an opening, the randomness for the commitment scheme. So these 3 values are concatenated and included into a puzzle. And for solving puzzle phase, again, given the puzzle solution, we can just parse it and extract required information, which is one of them is public key needed for the next puzzle to be solved. So given this one, the solver starts doing the squaring, and this is the base, so it starts doing the squaring to find the solution. Also, given the message and this opening, it can prove to the verifier who can easily check whether these openings match the commitment initially broadcasted by the client. So here in this example, I'm using hash-based code. So in terms of costs, the chain Timelock puzzles over a computation complexity of solving Z puzzles is equivalent to computational complexity of solving only the last puzzle. Also, solving puzzles imposes communication costs linear with the number of puzzles. So it is O Z, where Z is the number of total number of puzzles. So if you compare the number of squaring required to solve puzzles, the total number of squaring. So in our scheme, it is S multiplied by delta multiplied by Z, but in the naive scheme is much higher. So you may ask, why just comparing? We compare the number of squaring because, as you know, usually modular exponentiation is costly. So this is usually the dominant factor when we compare different costs of different schemes. So to give you just one concrete example, if you have 100 puzzles, then using the naive scheme requires 50 times more squaring than this chained Timelock puzzle records. So here is the table that summarizes the complexity of the cost of our scheme. So in terms of communication, as I mentioned, it is its complexity is linear with a number of puzzles, and in terms of the communication cost, the only especially for the verification, the only operation we do is during the commitment scheme. So if we use hash-based commitment, then we just invoke a hash function set times. And if we use Pedersen commitment, then we need to run 2z number of exponentiation, modular exponentiation. So it totally depends on the commitment scheme we use. So more or less, Timelock puzzle share the same applications with the original one. Here, the difference is we can encode more puzzles, more solutions into puzzles, so we can have better efficiency. For instance, we can gradually reveal multiple secret keys or multiple documents. Also, we can check whether a cloud server is providing service over a long period of time without the requirement that client needs to interact with the server. For instance, if the client wants to check the availability of secure hardware, SGX, or certain services like storage. Also, in this work, we gave two concrete examples of this chain Timelock puzzle. One is in proofs of retrievability, or POR, and the second one is a variant of verifiable Timelock, verifiable delay function with VDF. I'll briefly talk about each application. So proofs of retrievability is a crypto protocol that lets a client efficiently check the availability of data that is stored in a cloud server, where the cloud server can be malicious, is not fully trusted. So we wanted to design a POR scheme that offers the following features. First is outsourcing the verification. We have publicly verifiable POR, but in this scheme, in this publicly verifiable POR, the verifier has to be trusted with the correctness of the verification, but we didn't want to do that. Also, real-time detection. So if a proof is rejected, then the client is notified almost in real time. And fair payments, if the server is paid, the server is paid if it provides an accepting proof. And of course, efficiency plays a big role. So to achieve our goal, we combined the following primitives. First is homomorphic max and smart contract, blockchain-based random extractor, and chained Timelock puzzle. In this case, I must, in the parentheses, I must say, now I know your work, I think we could use your random extractor instead of blockchain-based random extractor. So in this outsourced POR, three parties are involved: client, server, and a smart contract. At a high level, they interact with each other as follows. First, the client encodes this file and also generates a set of parameters and some tags, permanent and disposable tags. The client generates a set of puzzles for the tags as well. The puzzle encodes the verification keys needed for the tags. It deposits in the smart contract certain coins that should be paid for and on a server for each valid proof. It stores all the data in the cloud. Then the client can go offline. At the time when a verification is needed, the server generates proof of retrievability or POR and sends the proof to the contract. Also, a bit later, the cloud manages to solve one puzzle and sends the puzzle to the contract. So even though here I'm showing that they are sent at the same time, it is not the case. First, the proof is sent, and then a bit later, the puzzle solution needs to be sent. The contract checks the messages correctness. It verifies the proof and the solution's correctness. The contract pays the server if the proofs and puzzles are valid. Otherwise, it notifies the client. This process goes on and on for many verifications. So it's not just one round. It can be, the client can be offline, and the server just proves to the smart contract each time a proof is needed. In terms of cost of these outsourced POR, as you can see in this table, the verification cost in POR doesn't involve any exponentiation because we use hash-based puzzle in this scheme. The setup in our scheme involves exponentiations to generate puzzles, but the number of exponentiation is independent of the file size and can be much smaller. Also, the proof size in our scheme is constant because we use homomorphic tags. But I don't know if we have time. If we don't have time, I can just briefly talk about this slide and then we can finish.
I think we still have time, so feel free to continue.
Sure. As I mentioned earlier, the chain Timelock puzzle can be used as a variant of verifiable delay function in certain cases, not always. So as you know, verifiable delay function is a crypto protocol that lets a prover generate a publicly verifiable proof asserting that it has carried out certain number of sequential computation. The number of sequential computation is defined and known to everyone ahead of time. So as I mentioned, the chain Timelock puzzle can be used instead of VDF to gain better efficiency in certain cases, not always, because VDFs offer some features that the chain Timelock puzzle cannot offer. So using the chain Timelock puzzle instead of VDF, a prover's computation cost will be reduced by a factor of 3, and its communication cost will be reduced by a factor of 6.5. So this table summarizes the chain Timelock puzzle's cost with other VDF's cost. So just 2 points. One is the proof size is shorter than the others. And the verification also imposes lower cost than the other two schemes. So to conclude, I briefly discussed about multi-instance publicly verifiable Timelock puzzle, and also discussed about its concrete instantiation, change Timelock puzzle, and discussed two applications of chained Timelock puzzle: outsourced POR and PDF. You can use the link to access our paper or the QR code. And that's it. And
okay, yeah. Thanks a lot for this very nice presentation. It was very great. So, and I'll stop now the recording and the live stream, and then we can go over to the Q&A session.